Hello guys, so today we're going to talk about streams. I do apologize for yesterday, I was a little bit off. I forgot to add the quiz yesterday and get the Kahoot in. So the quiz is open till 4 o'clock today. Try and get the Kahoot in as soon as possible. It will definitely help with some of the vocabulary terms that I will be going over. Okay, so most streams and river do not flow in straight lines. Here's an example. I don't see a lot of straight lines. Instead, they do something called meandering. It looks like a kind of a snake. I mean, look at that. Kind of snakish. Oh, pardon me. Oh, what's happened? Sorry. With a defined S curve. I mean, it looks a little bit like a couple of S's. In a meandering stream or river, you have an erosional and a depositional side as the water flows around the S curve. So there's going to be some sides that it's going to like wear away at the side, and then sides where it's going to add stuff to it. On the erosional side, the water is deepest. So on like the outer curve, it is going to be the deepest because it is moving faster. Think of it like this. Any of you who have run on a track or something, as you're going around the side, the person on the inside doesn't have to run as far or as fast to get around that curve. Now, the person on the outside, they have to like book it to keep up with that person who is spinning on the inside. Like if this one's just turning like this one is going to be like, has to go really fast to stay with it. On that note, the depositional side, so the erosional side is deepest and fastest. So the depositional side is going to be the slower or slowest side. And where the water starts to get slow, that's where you're going to notice that sediments fall out of the water flow, and they're deposited, thus being called the depositional side. Okay, so we're gonna look at my my lovely stream right here. Let me move my face. All right, we're gonna look at my my lovely drawing of a stream, and we're gonna answer some questions on it based on what I just said. You know, the erosional side, deepest and fastest. The depositional side is slower and shallower. So looking at that, knowing that, and that the outside, out is erosion, in is deposition. So which letters represent where the erosion occurs? Remember, the outside is deepest, fastest, and the inside is slower, and where the depositing is happening. And you should have A, C, and E. Those are the outside curves, the farthest side. So erosion is going to happen on that side. If that's the case, where is the deposition going to occur? B, D, and F. Okay, so let's look right here between C and D. Where's the water going to be the deepest? Remember, it's going to be the fastest. Oh, sorry, I keep doing that. It's going to be letter C. And if I look up at E and F, where is it going to go the fastest? It's going to go E because it's on the outside. All right, well, what's happening at this H? It's not exactly the perfect drawing, but it's kind of, what's it look like? Is it curving? Is it not? It's actually going straight. Okay, well, if I was to ask you to draw a profile or show you profiles, which do come up in the Regents, how would you draw a profile from points A to B. So remember, I'm going to draw a line straight across. That's the top part of the water. And then I got to figure out what side is going to be deepest. Well, we already said the erosional side. And the erosional side is ACE. So A is going to be deeper than B. So when I draw it, I'm going to draw it like this or something similar to that. That was the best I could do. All right, let's look at D and C. I'm going to go D to C. Which side is going to be the deepest? Remember, it's going to be the far side, the one that's on the outside. And in this case, the outside is C. So I'm going to go like this. And there it is. All right, let's look at E and F. What will that look like? Well, which side is the outside? The outside is E. So I'm going to go down and over like that. Oof, that was quite a down. All right, so GH to G or G to H. And remember, it's straight. So if it's straight, no one side is going to be deeper. So it's going to look pretty much the same, like, yeah, the same on each side. I forgot the terminology. All right. Well, now, I don't know if you noticed, like, things like this in this picture, or what looks like this. This is called an oxbow lake. So an oxbow was originally part of a meandering stream, but it got cut off due to deposition. So remember how on the inside of the curve, that's where all the depositing is going on. So say you have, like, even this, how it's going, and it must have curved like this. Maybe it curved over here, and then it curved and went like this. And this, all of a sudden, well, not all of a sudden, but over time, all the deposition started building and building and building and building and building. So what ends up happening is all this deposition, like right here and here, it builds up and it blocks the actual river that was previously there, causing, oh, I'm so sorry, an oxbow lake. It's just like, it's a lake that was, and I'm going to scroll back through a bunch of this stuff. Okay, so look at right here. This is a perfect example of an oxbow lake. So it curves up and around and down. It would have gone this way and this way. But because there was so much deposition going on, that it actually broke off and formed its own lake. Okay, so there's another landform or stream form that I want you guys to know about, and they're called deltas. So this is like a hand drawing of a delta, and this is a picture of an actual delta. So what's going on is deltas are sandbar-like islands that form when fast-running waters hit slow water like an ocean or a lake, and the sediments drop out. So, okay, so in streams, you've got fast and you've got slow. When you got fast water moving, it can pick up more and more particles and sediments. And once it hits, like, it's going really, really fast, say it's going downhill too, so it's even going faster, it's going and going and going, and then it hits the ocean or the lake, which they don't have a lot of movement in them. So it hits it, and it's almost like when you go on those water slides that you put your hands like this and it's just you, and I call them the wedgie makers. Once you hit that, because you're going down so fast, once you hit that bottom thing, you slow down, and as you slow down, like, all this water starts splashing out. Instead of splashing out, all this water is coming in and hitting the other water and slows down like that, and all these sediments just start dropping out. So you can see the stream, once the stupid thing goes away, the stream down at the bottom, it's coming out and it hits this big lake or ocean. It looks like a lake in this picture, and it's depositing all of these sediments that were in it, which forms like the distributionary channels, like where the water can get out. Okay, so that's a delta. And last thing we're going to look at is stream velocity. Okay. All right, I don't think I wrote on it. I did not. I apologize. This should say stream right here. So how fast the stream velocity, how fast a stream has to be to carry certain size particles. And this is on page 6 of your reference table, this right here. So this should say certain size, S-I-Z-E, size. All right, so I've gathered a couple Regents questions that has to do with this diagram, this table, this graph. All right, so you could be taking the Regents and it'll ask you, what is the slowest stream velocity necessary for a stream to carry the smallest boulders? So what I would do is I'd go right here to the small, like the lowest end of the boulders. That's the high end, this is the low end. And I would make a line with my paper, pencil, something with a flat edge. And I would almost like make a mark. So this goes down straight. And look, it's between 100 and 500. So I know it's between 100 and 500. So I can cross 100 out. I can cross 500 out. 800 is above both of them. So it's got to be 300. Well, why else? Well, it's about halfway. I'd say that might be 250. Could be 300 right there. Yeah, matches right up. Answer is going to be 300 centimeters per second. All right, what is the maximum size particle that can be carried by a 250 centimeter stream having a velocity of 250 centimeters per second? So I'm going to look down here at the centimeters per second again. And I'm going to find where I'd roughly say about 250. And that'd be, again, where I was before. So I'm looking and I see that pebbles right here. Pebbles would be like the maximum amount at 6.4 centimeters. Look at that. It's right there. I don't even have to do crossing out what I don't know. This is my test taking skills that I have. I try to eliminate what doesn't make sense first. So this one's pretty easy because you have nothing to eliminate. It basically gives you straight flat off the bat. 6.4. So it'd be B. All right, according to the Earth Science Reference Table, a stream flowing at a velocity of 100 centimeters per second can transport, well, let's look at the 100 line. It can transport pebbles, sand, silt, clay. Let's see which one has pebbles, sand, silt, clay. Silt, sand, pebbles, but not cobbles. Hey, guess what? I don't have to look any further because that's the answer. How about silt, but not sand? Well, no, because you have to have sand to have pebbles and cobbles. Silt, sand, pebbles, and cobbles. Cobbles are too big. Silt, sand, but not pebbles or cobbles. Yes, but no, because it can, no cobbles, but it definitely carries pebbles. Oh, pardon me. Oh, on my face. All right, and last one. According to the reference table, which stream velocity would transport cobbles but not transport boulders? So I'm going to look for cobbles but not boulders. I've got right here. It's about halfway. Anything above this side to this. So you know it's going to be under 500. Okay, I don't have to worry about over 100, so I can cross out 150. I'm stuck with 200 and 400. Remember, right about there was about 250. So your answer is going to be C. All right. Make sure you do the lab today and get that quiz in. If you have any questions, please Zoom or email me. I'll get back as soon as possible.